Hello and welcome to another video. In this video we're going to be working on painting the walls. So in this problem you're given two arrays, cost and time of size n, representing the cost and time it takes to paint n different walls. And there's two painters. A paid painter that can paint the wall in time I and that costs cost I, or a free painter that can paint any wall in 1 unit of time at a cost of 0. But the free painter can only be used if the paid painter is already occupied. Return the minimum amount of money that's returned to paint the walls. So basically, let's go through some of these. So the first example, index 0 and 1 will be paid by the paid painter, meaning these two, and it will cost 3, and during that time the free painter can paint the other two walls. So at the bare minimum, obviously the free painter can paint one wall when a paid painter paints a wall, but more often than that, it can usually paint more. So here, if there's only 4 walls, it's always going to be the paid painter will just paint 1 or 2 of the cheapest ones. So it'll be these two or these two, so 3 and 4. But essentially, how do we do this problem? Well, you could maybe think like, well, I want to figure out like maybe sort the costs or something, and then just like have the paid painter paint the cheapest stuff. But then the problem is that like the costs are associated with times, and it's kind of hard to get like a greedy solution. And the constraints are pretty small, so we're actually going to go with DP here. And I would encourage you for most of these hard problems, like your go-to solution should be DP. And so for DP, this is going to be, there's a few ways to do DP, but there's like one good way that I found that was pretty useful. So essentially, let's write down for our DP, as always, let's write down like our base cases and our stuff, right? So we need, for DP, we need 3 things. We need state, base case, weird. So actually, instead of doing that, let's do this. There we go. State, base case, and a recursive case. So what we're going to keep track of, and you could do a few things. There's 2 general ways you could do it. You could either keep track of like how much time the free painter has left to paint, right? And then what you could do is every wall, you could literally just say like, okay, I'll just have the free painter paint or the paid painter paint, and I can never have the free painter paint if he doesn't have any time, right? So that would look like something, let's say for wall 1, you choose for the paid painter to paint, then you're going to be like, okay, well, the paid painter will paint that one, it's going to be cost 1, and I'm going to add 1 to the time for the next state, because then I know like that the free painter will paint, we'll have like 1 more second to paint something else. And you keep doing that, and you can just like alternate and keep track of the time for the free and paid painter. But the better way to do this is we're going to keep track of actually the walls left to paint. And we're just going to say for every wall that the paid painter paints, we're just going to see how long that takes. And we're going to assume that the free painter painted that many walls. And then we can just keep track of like once we have no more walls left, even if we're not completely done with the array, once we've, our walls is 0, or in our case, we're going to start from 0 to n. So once we painted n walls, then we can just be done. So for our state, we are going to keep track of index in our array and the walls left to paint. Or I guess in our case, it's going to be walls painted. So this is what we're going to keep track of. And then we have 2 base cases. And so for those 2 base cases, yeah. So for the first one, we have no more walls left to paint, or all walls painted. Actually, we're going to do it this way. All walls painted. So we want to return 0 here, right? Because they're all painted, so we're done. The next case is we are out of bounds, but all the walls aren't painted yet, right? We did some format where all the walls aren't painted. We would want to return. So if we're trying to minimize, this would be a state we'd never want to have, right? Because we want to paint all the walls. So here we can just return infinity. And that would handle both our base cases. And then for a recursive case, once again, a little bit weird, but we're going to have 2 cases. And it's either going to be the paid painter paints, and then let's calculate how many walls are painted. And so the way that's going to work is it's going to be, first of all, the cost is going to be cost of the index plus dp of the next index. And the number of walls left to paint is going to be walls minus 1, because the paid painter painted 1 wall, minus the number of walls that the free painter can paint during this time. And how many walls can the free painter paint? Well, it's going to be time of I, right? So So if it took like 5 for the paid painter to paint 1 wall, that means the free painter can paint 5 walls during that time. So that's going to be one case. And then the other case is going to be do nothing, pretty much. And then that's just going to be dp of I plus 1. Go to the next one and walls. And the reason why you can do nothing is, let me show you here. Let's say we do have like 5 walls. So if, let's say they all have cost 1, just in our basic example, if the paid painter paints a wall, like let's say we are over here, we're in this DP, and the paid painter decides to paint this one, and we have 5 walls total. If the paid painter decides to paint a wall, now the free painter can also paint 1 wall during that time. So now our walls goes down to 3, right, for the next state. And then over here, even if nothing is done, the free painter painted somewhere, but this allows us to like not pick exactly where they painted. We can just say like, okay, we picked exactly where the paid painter painted, and we know how many walls the free painter painted. So we can just pick whatever the paid painter paints, and then the free painter can just paint the rest. We don't necessarily have to say which ones, because it's like, so one person has to paint it, right? So if the paid painter doesn't paint this, then by default the free painter painted it. And then this part would allow us to make sure that the free painter only works while the paid painter works, right? So here we can say like, okay, yeah, let's do nothing. Then we come over here and maybe we'll say like the paid painter paints this one. So that also gives the free painter time to paint 1 wall. So we have 1 wall left. Then here maybe we do nothing. And then here the paid painter paints. So now we have -1 walls left. And then here we would return something. So essentially for this kind of solution, the free painter would have painted these 2, even though we technically did nothing in our algorithm once we were here. We're essentially saying they're going to paint at the same time, and this will ensure that they paint at the same time. And that's pretty much it. So like this is all we need, and then we can just return the minimum of all these things. So we're going to have a visited set, and we're also going to like get the length of the number of walls or something. So you can call that like W maybe or something. It's going to be a length of cost. And then we're going to have a visited hash map. But actually, instead of a visited hash map, what you can also do in Python that I haven't really done much, but you can just do this. And then this will make a cache decorator over whatever function you have, and it'll automatically cache stuff in it. So you don't need like the visited or check if things are in visited. This will handle it all for you, which is kind of nice. So we're going to have def dp, and we're going to have 2 things, right? We're going to have an index, and we are going to have a walls left. So we'll call that walls. So the first case we're going to handle if walls is less than or equal to 0 means in our case it's going to be greater than or equal to W, meaning we've painted every wall. And this can be greater, right? Because let's say you have 4 walls, but the time for 1 wall is like 1,000,000, then you're going to add 1,000,000 to your walls, which will be greater. But that still represents every wall being painted. So here we want to return 0 because we're done. Otherwise, if I equals W, that means we've went through all our walls, but we haven't painted them all. We still have walls left over. We can return infinity here. Otherwise, we can just return the minimum of, so what's the cost of painting? Well, it's going to be cost of I plus dp of I plus 1. And then for the walls, it's going to be the walls minus 1, right? Because the paid painter painted 1 wall, minus how many walls did the free painter paint during that time? It's going to be time of I, right? Whatever the time is, the free painter can paint that many walls. And I believe that's actually it. So we can actually just return here dp of, actually, so instead of minus, this needs to be plus because we are adding to walls, right? So we're saying if every wall has been painted. So it's actually going to be the other way around. So we're going to start at index 0, and we're going to start at wall 0. Yeah, let's try that. Let's see what error we have. Probably just some kind of parenthesis thing. But let's take a look. Let's go back. Int is not iterable. Okay. Cost I plus dp I plus 1 walls plus 1 plus time I. So we have the comma here and here. I think we have, oh, do we have too many, no we don't. Oh, right, we don't have, okay, I see what we're missing. So this is the cost of our painter painting, but we also have to have the do nothing thing, right? So do nothing is just going to be index plus 1 and walls. And so now we can try it, and that does work. Yeah. And so what I will mention is you can space optimize this, because you can see that like for every dimension, you are going down one row only, right? Like you're doing DPI plus 1 here. So whenever you see these things, whenever you only go DPI plus 1, you can space optimize this by doing a bottom-up DP, and then you can get rid of this I dimension. And so I will briefly show you the code for that, but I'm not going to like walk through the steps for it because I've done this in like 10 other problems. So if you literally look in like any DP problem I have, you can do this. And it takes like 20 minutes to do it, so I don't want to make the video too long, but let me show you the code here. So essentially, if you look, here's our bottom-up solution, and here is our space optimized solution. And the code is pretty similar, right? You make a 2D array for one of them, and then you return the 0th element. And then for the space optimized, we just get rid of the dimension for the index because you're only relying on the one below it. So for every single row, you just make a new DP, right? You just make a one-dimensional DP, and then you fill it out, and then you set your old DP equal to the new one. So essentially, it would be like, imagine if you had a 3x3, like 3x3 like this. You had a 3x3 array here. Let's say that this array had some elements like this, right? So this is a 3x3 2D array. Now what you do is you only make this one array, and then let's say you want to make this, you just make a new array, and then you get all the elements from the one below it, and then you replace it, right? So you're essentially like looping up where you're only keeping track of 2 arrays. So you'd make this new array, you would replace the old one, and then this would be like your new array, and then you'd make another new array, and so on, right? But you just keep making a new array every time, and you only have 2 arrays instead of a whole matrix. So if this was like n by n, now it would only be n space. So we can talk about the time and space for all of these, I guess. So essentially for the memoization, or for both of them, we're going to have an n-squared solution because we need to keep track of the I and the walls here. And so these are the same dimension, right? I is length of cost and walls is the length of cost. But for the space optimized solution, it will be O of n, where the memoization will be still O of n squared because you do have this cache or this 2D array. So that's like, I think what I'm going to do in future problems is just point out where you can bottom-up optimize, but I'm not going to walk through the whole thing there because it's like doing the same thing a billion times. But if you want to look at some of it, like if you just look at a bunch of my other videos, I think half of them have like a space optimized solution. So you can do that. But yeah, that's going to be all for this one. So hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.